Welcome back to Hate Sparsh. Today we are tackling Leetcode 2196, create binary tree from descriptions. Here we can see we are given a 2D integer array descriptions where description I is a list of 3 values which is parent, child and is left. And parent I indicates that parent is child, like parent I is parent of child I in a binary tree where binary tree have only unique values. And is left indicates that the child I is left of parent I, like this is parent and child is left of binary tree, or this is parent, child is right of binary tree. So if it is left, then the left I is 1. If it is right, then the left I is 0. Now what we need to do is we need to construct a binary tree described by description and return its root, which is this. And like the test case is which will be generated such that the binary tree is valid. So we are also mentioned that the binary tree will always be valid. So let's just check into one problem first, that we are given a array 20, 15, 1, 20, 17, 0, 15, 21, 50, 80, 0, 80, 19, 1. So now what does this mean? That 20 is parent of 15. So 20 is parent of 15 and it is the left side. So this is correct. Now 20 is also parent of 17, which is its right side. So now in binary tree, only parent can have two children, either left or either right. So we got to know that 15 was the left one, then 17 was the right one. Now again we are given another value where we are given 50 is parent of 20. So 20 is this node and 50 is parent of 20. Similarly, 50 is also parent of 80, which is not right. So 50 is parent of 80, which is on the right. Sorry for the mistake, like it's not left and hence right. And similarly, 80 is parent of 19 and it is the left node. So this tree is clear and hence we are just providing the output, like we are just returning this node 50, which is the root node, and then this output is what, like the Leetcode will be calculating it automatically. Similarly, let's just take a look into example 2. We are given, if we will just ignore this part, what we can see is that 1 is the parent of child 2, which is left child. Similarly, 2 is parent of child 3, which is its right child. And 3 is parent of 4, which is its left child. And hence, we got a somewhat of a skewed tree only, where each node is left, right going down below, and we will return this root. We have to return this. And Leetcode will automatically build this like this. You can see 1, it's left child, it's right child, then again it's left child, it's right child, and then again it's left child, which is 4, and hence the tree is valid tree and we successfully created. So a very quick approach like which comes into the mind is, why not just take all of these values. We know that this is parent, this is parent, this is parent. Similarly, 20 is parent, 50 is parent, and 80 is parent. We'll just take these values and just create a hash map of it, and we'll just store these values, like we'll store the child values against the hash map. And hence by using this brute force technique, what we are going to do is, we first created a hash map of, this is, you can say, parent node, which maps to the childs which it can have, child 1 and child 2. One can be null also, which we can determine from here, basically from the isLeft parameter. And similarly, now after constructing the whole hash map, the only problem which right now which we have is to find out the root node. Root node is basically the topmost node of the tree. So to find out the topmost node, what we can do is we can also have a set in which we will be adding all of the child nodes as well as like we'll be having all the child nodes, and similarly we can again have a set where we can have all the root nodes. Now here you can see if a if a node is present inside a child, let's say take example 2, this was a child node and this is also a parent node. So if this parent node is present inside a child, that means that specific node is not a root node. And hence we know that if a specific root nodes, or we can say parent nodes, is not present in child nodes, then we know that that is specifically a root node. And after that, what we can do, we can just recursively iterate over the hash map, and then we'll just construct the tree, overall tree. So just this is a very basic approach which comes to a mind if we are, let's say, in an interview. So let's just look at the constraint ones, that if we are, let's say, using this approach at all, then will we be able to solve this question like with this approach. So the constraints given to us is that description length can be of 10 raised to 4. If it is can be of 10 raised to 4, then there could be a case where, let's say, the tree is fully skewed like this example 2. So this is there. And second is descriptions length is 3, which is already defined, that parent, child and the is left part, and parent and child is lying between 1 to 10 raised to 5. So all these values which is inside the node can lies from 1 to 10 raised to 5, and is left is 0 or 1. 0 means is right node, 1 means is left node, and binary tree is valid. And hence we know that if description length is 10 raised to 4, we can at least go 10 raised to 4 call stack deep using recursion, and hence we will be able to construct this approach. So during an interview, what we can do is we can see that this create binary tree is the function which is given to us by Leetcode itself, where the descriptions is passed. So what we have taken is we have taken unordered map of nodes, and then we also have taken unordered set of parent nodes and child nodes. Now what you can see here is we are just iterating over the descriptions, and we are inserting values into parent nodes and into child node. Descriptions I0 is what? Descriptions I0 is the parent node and descriptions I1 is child node. This we'll use on later to find out the root node. These values we'll use to find root node at a later point. Now what we need to see is we'll check if this nodes basically which is holding that okay, this specific value, this specific parent node does have any child node or not. We are checking if this parent node exists or not. If parent node exists, not equal to node ends means it exists, then what we are going to do, we are just going to check if it is a left node or right node with descriptions I2. And if it is a left node, what we are going to do, we are taking descriptions I0 is the basic parent node, and at its left node we are going to append this description I1. So here it will contain the left child, and here it will contain the right child. So we'll do it for both. Let's say if we are not finding, let's say, and if we are able to find this specific node, what we are going to do, we are creating another vector of value 2 with both the childs as -1, because we are taking child value as -1. We could also have taken it as 0, because we know that the value can never be 0 because it lies from 1 to 10 raised to 5. So we could have taken any of them, and depending upon if it is left or right, we are just populating the value. If it is left, we are populating value 0 as the value child node. Description I1 is nothing but child. And if it is right, then we are just populating this child onto the right value, that value 0. This was the value 0 and this is value 1. And similarly, now what we are going to do, you remember that we are adding nodes and child nodes here. So we are now moving, like traversing the parent nodes part. This is parent nodes, and we are checking if that specific parent node is present inside child node or not. For any parent node, if it is not present inside child node, we know that okay, that specific node is a root node. Now let's create another function which is build binary tree, which we have discussed here, that it will recursively go over the whole hash map and create a tree for us, and we are going to return a root node. So build binary tree, you can see the return type is tree node star, and what it is taking one parent node, and it is taking the whole hash map of the nodes value which we have created here, an ordered map. Now what we are going to do, if let's say for any parent node we are not able to find out any, for parent node, let's say this is a parent node and we are not able to find out it in child node, that's what does that specifically mean? That it is a child node itself. What does that mean? That it don't have any additional childs. Then what we'll do, we'll just use this constructor, this constructor, and we'll be just using the value x, which is value of parent node, and left and right pointer will be null. So these are null pointers, and hence we know that this is a specific child node. And now for every, like we need to construct left tree and right tree, how recursion works. So we are just creating left tree and right tree, and we are checking, because we have taken here as root node as -1 does means that it don't exist. So if it is don't exist, we are appointing left tree to null pointer, right tree to null pointer. But let's say if it exists, then what we are doing, we are just passing it that okay, take its left value is this value 0, take its left value and construct the node recursively. It again goes into this function, again check if it is the last node or not. If it is a last, basically terminal node, then we point it as child node and we create a left tree recursively. Similarly, we are going to create a right tree recursively, and once these two trees are created, we are now going to create a full tree node where each, like where it will take parent node, like from this constructor, where it will take parent node as the current node value and its left tree which we have computed at line 19 and 20, and right tree at 22 and 23. So let's just take example of this, like 50, 20, 18, 15, 17, 9, this one. So now I'll just write it down quickly, that how our vector nodes hash map actually look like. So if we are talking about hash map, when we are constructing the hash map, it will look somewhat like 20 is a parent node and 15 and 17 are its child node. 15 is left, 17 is right. So 20 is the parent node, 15 is left and 17 is right child node. Similarly, we went to the index I equal to 2. 50 is a root node for both of these cases, and 20 is left and 80 is right node. So we'll just now add it. 20 is left and 80 is right. Now we again go back and we see okay, 80 is also a root node and 19 is only the left child node. So here we come back, 80 is the what was the left node? Left node for 80 was 19. So 19 is the left node, but right node is -1 because we are creating, you are seeing that we are creating -1 here. So this is a hash map which we found out. Now from this hash map itself, like parent nodes, like what will be the parent nodes which are present on description I0, which will basically be 20, 50, 80. Only these three can be the parent nodes. Similarly, child nodes can be what? Child nodes can be all of these values. So child nodes will consist of 15, 17, 20, 80, 19, but not -1 obviously, because you are seeing that every description I1 is basically a child node itself. So now we are iterating to parent node and we are seeing if 20 is present in child node or not. 20 is present, we just move on. We see 50 is present in child node or not. 50 is not present, so we have taken 50 as the root node. We now know 50 is the root node. Now in build binary tree, I'll just do one recursive step here. Let me just erase some of these values. So here 50 was given to us as parent node and the node is also given to us. Now what we see, if 50 is 50 the nodes and like is 50 present in this hash map or not, we found out okay 50 is present, so this condition was true. So now what we did is we created two nodes left and right and we checked if parent node 0, basically 50's left is -1 or not. We figured out that 50's left is not -1. So what we did is we now pointed 20 as the root node, and what this function is will do, it will try to construct a tree which has a root node of 20. So now 20 is passed to this value, now by 50, now it will be passing 20, map will remain the same. Now what will happen, it will check if 20 is available here or not. So it sees okay 20 is also available, 20 is available, and hence it returns true. Now 20, it will see that okay if 20 is left is -1, it is not -1, and hence it will again try to build binary tree. So it is again calling it with the value of 15. So now this calls the value with value of 15. We are basically doing a DFS here. So 15, now 15 it is also trying to find 15 here, but now as you see 15 is not present. So it will say that okay for 15, node number 15, it don't have any child, this don't have any childs, so it will just create a tree node 20 and return it back. So left tree will become 15. Similarly it goes to right tree, so right tree of 20, so 20 right was what, 17, so 20 right was 17. Now it goes to 17 and similarly it found that 17 also don't have any childs. So what it will do, now it will create a tree node, parent node, which have left tree as 15 and right tree as 17 for node number 20. So 20 left is 15 and right is 17. Now it will assign this value to what, left tree, and left tree will again check the right tree part. So 50's left was 20, we will now traverse to 50's right, which is 80. So 50 will traverse to 80, and in a similar manner we'll see that okay this is 50, this is 80, and 80's left is 19, so 80's left is 19, but 80's right don't exist, and hence we'll create. So now coming to the time complexity and space complexity here. So if you'll see, the time complexity is O of n. Why it is O of n? Because adding anything inside map or reading a map is always a O of one value. So wherever you are going to see, it is, we are just traversing over descriptions, which is again n. We are inserting and trying to find which is O of 1, and that being done O of n times, and hence this for loop will take total of O(n) operations. Similarly, parent nodes can contain exactly n-1, not more than n-1 values, and hence this loop will also take at max of n iteration, like n-1 iteration. So we can say amortized time complexity of O(n). Now similarly going to build binary tree. Now build binary tree will basically recurse into every parent node. Now parent node is this top part, basically this 50, we can say it is the parent node, and what it will do, it will try to go into all the nodes. And how many nodes do we have? We have a total of n nodes, and hence this will also go take O of n time complexity, and hence the time complexity of O of n. But what about space complexity? Here you can see that we have created an unordered map of nodes which can take space complexity of O of n, and we also have created an ordered set. It will also create time space complexity of O of n. Now here we are just assigning values, so no space complexity going here. Similarly, root node is O of one space, so we are not concerned because root node is what we actually need to return, so it is an int value. We're not concerned about it. But now in build binary tree, you can see that what is the call stack space which it is taking. You are seeing that we are creating this as O1, left tree O1, right tree O1, tree node O1, nothing else. But whenever like the stack goes like, it goes into O50, then this stack gets maintained. It goes into 20, this stack gets maintained. It goes into this 15, again this stack gets maintained. So let's say for a totally skewed tree, maybe the tree is like 50, 20, 17, 19, 80, like this, the total space it can also take is O of n, and hence space complexity will be O of n. So we see that the time complexity and space complexity for this, I'll just write it here, T is O of n and space complexity is O of n. Now solution 2 is nothing, just like in an interview, you're anyhow not going to modify anything in this, either you are going to change your approach, but let's say during an interview you should have thought of some of the things. First thing is, why are we like even using vector here? Because we know that each node can have left or right, then we have replaced the vector with pair to just reduce onto some of the time complexity part, because vector is created dynamically and we'll theoretically save on to some time complexity. Similarly, you can see we were earlier having two nodes, one was parent nodes and one was child nodes. Why to maintain two nodes? We are keeping a child node itself here. Now third thing is, just to make solution more elegant, what you are seeing here is I am always using description I0, description I0, description I2, description I0. I am using these value repetitively. So ideally what should I have done? I should have taken it into different variables that I know description I0 is parent, description I1 is child, and description I2 is left. So now for child nodes, I now need to figure out that, okay, what node is a root. I'm still adding child nodes into the child into the child nodes, and on the basis of is left variable, I'm saying node parent, like this node left is child or this node right is child. Right is child, we can just write it left. So where do we need to assign it? So again, similarly what it did, it created a hash map in a similar fashion like what hash map we had 20, 15, 17. So 20, 15, 17, and then 50, 20, 80, and at last 80, 19, -1. Now here you are seeing, earlier we were assigning it as -1, but here we are using default value, so it will become 0. So now for how will we calculate that, okay, which is the root node, because now we don't have any of this like parent nodes unordered set. Now what will happen? We'll just iterate over the description. Descriptions have all of the nodes which we are going to add. Now descriptions, like the value 0 was the parent node. So parent node is what we are actually storing here. If you'll see, we are only adding descriptions I0 here. So what now we are going to do? We are traversing over descriptions. We are finding that okay, child node have that value or not, this parent node or not. If it don't have this parent node, then that means that okay, root node is this specific parent only, and hence we'll pass this root node here. Similar to what we are doing here is we are checking child node have this parent or not, and then we are going to pass that root node here. And similar, and here we are just using exactly the same thing, that okay, if parent node is equal to n, that is the tree node. Left tree, we like earlier what we were doing here is we have just used left tree and right tree and have we are assigning null pointer it to like at a later point in time. So now we are by default assuming left tree is null and right tree is also null. And if we are seeing okay, if the let's say if the parent left like this left exists, then it will be build binary tree of left node whatever it is. Similarly, if right exists, then we'll build this tree. But if let's say left don't exist, then this connection will be null forever, what we are setting here like from this place. So this will be null forever, and this is the exact same thing which we are returning. So time complexity and space complexity will remain still the same. Time complexity will be same because you are seeing that we are using the same for loop here as well as here, as well as this tree node build binary tree is also running the same time. Now coming to the space complexity, you can see that we have what we have done. We have removed this parent node from here. Also we have removed vector from here. But still nodes, child nodes, the stack trace of this will still take space of O of n as we discussed earlier, and hence time complexity and space complexity will still remain O of n. So now let's jump into like in an interview what interviewer can ask. Interviewer can say okay, you have done this with recursion. Is there any way possible that you can eliminate the recursion stack entirely, or maybe you can do it in single pass or double pass? Here what we are doing, we are iterating it in one pass, then second pass, then we are iterating it recursively. So interviewer can ask different type of questions. So now comes the most beautiful answer here, which is what we are doing earlier was we are creating nodes, like we are storing all the nodes here. Nodes as in nodes means nodes value. We are storing nodes value here, and after we have all the nodes value, we are passing it to this recursive function and saying okay, just build a tree for me. Now here what we are going to do, we are creating the node itself, not node value, at the starting of the loop itself. So now what we are storing, we have a map of int and tree node. So earlier what the map was, it was basically int of parent. Parent was storing its left and right. But what it can do is now this specific value have a tree node. Tree node can have left or right, or it can have a whole tree also, not only left right. So we are storing it at runtime itself, like at this function itself. And similarly, we have another set of children which we earlier also have to just figure out what is the root node which we need to return. Now similarly, we went into this function descriptions.size, which is nothing, and we have extracted the value, that parent value, child value, and if it is left or not. And inside children we have inserted the child value because we need to find out what is the root value. Now comes these three parts are the most important here. Now what we are seeing, we are checking that node map have this parent value present or not. If it don't have this parent value present, what we are going to do, we are creating that specific node. So let's just take this example again, 2015 1. So we are checking if 20 is present here or not. We see 20 is not present, so we have created 20 as a new node. 20 has left and right as null pointer for now. Similarly, now we are seeing that okay, for child value was for what, for 20, the child value was basically 15. So we are checking for 15 too, that okay, if 15 exists in the node map or not. So for 15 also we see that okay, it don't exist. we created 15 node also as null pointer itself. Now we checked that okay, if it is left or not. We see that for 2015 it was left. So what we did was we actually go to node map of parent value. Node map of parent value is this, and it's left, basically it's left which is pointing to null pointer. We are now pointing it to 15. So now we got a tree itself where 20 is left is 15, its right is null, and 15's left and right is also null. Now we again move into this loop for int I equal to 1. Now what is int I equal to 1? I equal to 1 is nothing but 20, 17 and 0. So for now again for 20, I tried to find out if node has value 20 or not. It found out that okay, 20 already exists. So we don't need to do anything here. Now it tried to find out 17 exists or not. So it said okay, 17 don't exist. It created another 17 node which is pointing to null. And then what it does is node of parent val, basically node of 20. Node of parent val is this 20. It said okay, its left is child val 15, but 2017 was 0. So is left is condition is false, and we went to second. So what we did, 20's right is 17. So now 20 left is not pointing to null and it is pointing to 17 instead, and hence we got this tree. Now again traversing again, what we did is we found the value 5021. So we'll just go and we see 50 exists or not. 50 don't exist. Now we see 20 exists or not. We see 20 exists, and we see is left is true now. So as is left is true, we say that okay, node map parent left, basically node map parent is 50, 50's left is 20. So now instead of pointing 50's left to null, 50's left is now pointing to 20, and 50's right will still point to null. Similarly, we will create the whole tree in this way. Now going again to this function, this is pretty standard function which we have discussed earlier, that we are going to all the descriptions value, basically the parent values, and we are seeing which parent don't exist in these children values which we are inserting here. And hence for the value 1 minute 50, we see that its value won't exist in any of the child node, for any of the child nodes, and hence we'll be returning 50. So now let's check its time complexity and space complexity. So if you'll see, time complexity for this will still be O of n, because we are traversing descriptions.size here also, and we are also traversing full descriptions here. So time complexity will still be O of n, but where it have resulted in a saving is the space complexity part. So now earlier you were seeing we were having what? We were having this unordered map, this unordered set, and these are nothing, and this call stack ka space. But here if you see, we are having this unordered map, we are having this unordered set, but we don't have any recursive stack. Recursive stack is not present, and hence space complexity will still be O of n, node map plus children, which is O of n plus O of n plus O of 0, because this recursive stack don't exist. So space complexity will still be O of n, but now we are not at a risk of basically exhausting our call stack value, because that is also a significant value. O of n plus O of n plus O of n, amortize we count it as O of n, but this is what we can achieve at our best. So time complexity is O of n, space complexity is also O of n, and this is the best which we can achieve. And hence that was all, like how we can solve this problem. Thank you for watching Hate Sparsh. Please do like, share and subscribe.